Hello, everyone. Welcome to this hydrogen seminar series between Cardiff University and University of Wyoming. I'm Mason Qatardon, Professor of Energy Systems and Network at Cardiff University, and today we have Dr. Danny Pudjianto from Imperial College London that is going to give a presentation on a holistic approach to empower hydrogen supporting net zero. Danny is a senior research fellow at Imperial College London and have been working on energy system modeling for more than 20 years. I have privilege of collaborating with Danny in High Act project, which is a hydrogen system integration of hydrogen hub funded by UKRI. So Danny is going to use the next 30 minutes going through his slide and talking about a recent research project they have completed, and then we will have time for question and answer. I would like to encourage participants to use Q&A features in the bottom of the screen in order to write down their questions, and then we will pick this up after the presentation. So, Danny, I'll pass to you. If you're ready, please make it stop.
All right. Thank you very much, Mason, and thank you for inviting me. I'm very happy to share the kind of the research findings that we have carried out at Imperial, and just to have to greet you also, everyone who listened to these presentations. The title of my presentation today is a holistic approach to empower hydrogen supporting net zero. This is based on the studies that I carried out with my colleague, Dr. Hossein Ameli, and also the Professor Gordon Serbak at Imperial College London. Yes. Okay, so the content of my presentation today, I will start introducing the key challenges about the hydrogen, overview of the methodology and the case studies that we carried out, and some key findings and the conclusions. So when we heard about the hydrogen, so many studies focuses the hydrogen as an alternative energy carrier to decarbonize the energy, as an alternative to the electrification. But hydrogen also have other roles that should be recognized. For example, like the hydrogen technologies can provide the flexibility to the electricity systems. Hydrogen also can provide some means to support the energy system security and resilience, and also the interaction between the hydrogen technologies with other low carbon technologies can also minimize the energy system costs. So these roles sometimes are not looking as in a holistic manner. And the key challenge, one of the key challenges in the hydrogen at this moment, why it has not been growth as other low carbon technologies like renewables, solar PV, and so on, is that there are some lack of clarity and uncertainty about these hydrogen roles, demand and application, and also the economics of the hydrogen economies. And studies about the role of hydrogen often do not consider the integration with the other systems, such as the heating. With the electricity, there are many studies between integration of hydrogen and electricity, but sometimes it doesn't consider also the impact on the carbon capture, storage infrastructure, and other flexibility technologies. So we think that in order to capture the whole system value of the hydrogen, we need a holistic approach to capture that. So this is just to give the result of the studies that we carried out, analyzing two cases. One is the electricity system and the hydrogen system, but planned sparingly. So it is what we call it a silo approach. So when the electricity system, basically there will be no hydrogen technologies in the electricity system, no electrolyzers or the hydrogen power generations. And compare with that when we integrate the hydrogen and electricity together. So we call it the integrated approach. And we evaluate the cost of this annual system cost of these two systems. And here we found that with the integration of the hydrogen into the electricity system, that can save the system quite substantially, which is around 5.6 billion pounds per year. And the savings come from, if you look at on the diagram on the right-hand side, the negative value there reflects the savings that the system can obtain with the hydrogen technologies. But on the positive cost is that the additional infrastructures that need to be built in order to support this hydrogen technology. So with the hydrogen technologies, for example, like with the electrolyzers and the hydrogen power generations, that will require additional low carbon technologies. If you can look at the pointer here, low carbon technologies and also some other additional picking plant and the electrolyzers, while it offset the need for the fuel in the power generation technologies in the power generation production, and also reduce the carbon, the cost of offsetting carbon emission through negative emission technologies like direct air carbon captures and storage. And it also, because it reduced the use of gas, it also reduced the carbon storage costs, and also reduce the need for the hydrogen productions from the fossil fuel base. So the savings are quite significant compared with this additional supporting costs, and this result in the 5.6 billion net saving. So we can also see from these slides that by integrating the hydrogen technologies like electrolyzers and the hydrogen powers, we can see that the system can accommodate more renewables energy source, like the offshore winds, which increase from the 86 gigawatt to 120 gigawatts. But also displacing, for example, the gas CCS. So the gas CCS in the system where there is no hydrogen technologies, the system will require like a 30 gigawatt, but then we can displace totally with the hydrogen technology. So it's reduced to zero, while increasing the need for the hydrogen power generation in that context. So how we should analyze the system with hydrogen. So in here we have developed a model called integrated whole energy system models. In here, it is a very large optimization problems which try to minimize the overall energy system costs, including the electricity, gas, hydrogen, heating, and also the CCUS infrastructures. But we take into account from the supply side and also the energy network up to the demand side, but also take into account some flexibility technologies such as demand side response, flexible generations, interconnections, and also storage. We also model in sufficiently the spatial granularity of the demand and the energy resources in the GB, and also the interconnection between the GB and the Europe and the Ireland. And one of the quite unique model of this, the tool that we have developed, is that this also include the distribution, where we try to represent the distribution networks into two types of distribution network. One is the rural and urban, in order to analyze the impact of the hydrogen technologies or other low carbon technologies that are connected to those distribution networks. Because the impact is not only on the local distribution system, but also will also affect the the upstream system. The modeling is also take into account the operational requirements from milliseconds time frame, like the frequency response and reserve and so on, up to the multi-year investment program. So because there are some very strong link, especially in the future, where the flexibility will be quite needed in the system, that the operational flexibility has to be captured by the sufficient investment in the flexibility technologies as well. So this is just kind of like a list of the input data from the tool that we use. So we take into account the load profiles for years, for a different type of energy demand, like electricity, space, and hot water heating, transport, and for both domestic and non-domestic sectors. We take into account all the technologies from the power generation, hydrogen production technologies, hydrogen storage, hydrogen transport, and so on. And we also consider this the CapEx and OpEx of all of those technologies. We also take into account the constraint associated with the scenarios that we try to analyze, for example, with the emission target or the policy with the export-import of energy policies. Now the output data, so from the modeling here, what we are after is to understand what are the optimized multi-energy infrastructure portfolio that will be proposed by the models. How this is the multi-energy operation should be coordinated. And then, of course, we can then evaluate the techno-economic performance of the technology, the fuel usage, how much carbon has carbon captured and storage will be, and the residual emissions that need to be offset, energy exchange, capacity sharing cross region, and also the flexibility technologies that need to be deployed, considering all this multi-energy sector coupling flexibility. Now for the case studies, in here we focus on the 2050 energy scenario, future energy scenarios. We take into account from one of the national grid future energy scenarios called Leading the Way, which has the most ambitious target in the renewable energy, and then the customer participation in providing system flexibility. In preparing the scenario, we understand the requirements for the system in order to meet the kind of like the extreme events, which happen very rarely, but need to be considered in the system planning in order to ensure that the sufficient capacity, energy system capacity, will be provided to meet the peak demand, and that to withstand against that kind of event. So we have inserted few days very cold condition with low renewable energy sources to test the system as resilience. And in that context, we can then evaluate the role of the hydrogen also in providing the system resilient to the system. And then there are a number of some details like that. There are, of course, some sectors which are hard to decarbonize, 50 megatons CO2, that will require some negative emission technologies to offset the system. And this will come, if I will tell a bit later on, will come from the bioenergy with the CCS, which produce the hydrogen. So there are some role associated, some role of hydrogen that can deal with that requirements. And we focus on the two core scenarios. So in the rest of the study, except the last one, the last slide later on, I will talk about two core scenarios, which are about the scenario with the hydrogen for heating, where 2/3 of the domestic customers in the GB in 2050, their heat demand will be decarbonized using the hydrogen boilers, while the rest will, for example, for the off-gas grid customer, will use the electric heating. And the second one is the full heat electrification. And the reason why we choose this scenario is that there are many studies outside there which tend to discount the use of the hydrogen for domestic heating because of the economic reasons, because of the efficiency of this hydrogen boiler is much less compared to the heat pumps. Then therefore this option should be discounted. And we disagree with that, because then we say that there will be some synergy associated with this hydrogen heating with other hydrogen technologies, and within the interaction of the whole energy system studies. So in both scenarios, 20% heat supplied by the district heating, and there are a number of sensitivity studies, which I will show the result later on at the end of this presentation. And on the left-hand side, there is a kind of the energy demands has been taken into the studies that consist of the heat demand, electricity demand, and also the hydrogen. So the key question here is that what is the optimal portfolio of the energy sectors, particularly hydrogen? Because with the analytical approach that I just presented, all the low carbon technologies will compete each other. So if we put the hydrogen technologies in the model and it is selected, which means that this hydrogen technology is quite competitive against other low carbon technologies. And the second one is that what are the whole system costs, especially comparing these two scenarios, and what are the key drivers for low cost energy system, and how robust are the solutions. And this slide shows the hydrogen portfolio of these two core scenarios, this hydrogen for heating, H2, and then full heat electrification, ELEC. And you can see that there is a hydrogen power generation technologies, which is a hydrogen CCGT and hydrogen OCGT, have been proposed by the model. So there are some capacity that appear in the model, which mean that they are quite competitive against other power production technologies. In addition, there are also some hydrogen production technologies, like using the autothermal reformers and the CCS produce the blue hydrogen, and also the electrolyzers produce the green hydrogen, and also the hydrogen comes from the biomass energy with the CCS, plus some hydrogen storage, as you can see. And then the last two columns in the table show the utilization of these hydrogen assets. What we can learn from the result of this study is that their hydrogen technologies are actually quite competitive against other low carbon technologies, because the model actually show that we require this much of the hydrogen technologies in order to minimize the overall system costs. And there are around 104 gigawatt of hydrogen power and production capacity proposed here, irrespective whether it's hydrogen and hydrogen for heating or the hydrogen or full heat electrification, and around 6.4 hydrogen storage needed. And this shows that it is a massive challenge in producing that such amount of the capacity for the 2050 in order to achieve this net zero carbon target in the UK. There are only around 26 more years in order to build such infrastructures. And what is another interesting insight from the study is there is a trade-off between the hydrogen power generation and the hydrogen heating. So in the hydrogen heating scenario, we see a much smaller hydrogen power generation required compared with in the full electrification, and that shows that with the hydrogen heating, that actually reduce the electricity peak demand, which then of course will have impact on the electricity infrastructure required. Another finding is that in the utilization of the hydrogen assets in the hydrogen for heating, in the first scenario, is much higher compared that with in the electrification scenario. So this means that although the efficiency of in the hydrogen for heating is lower compared with the full electrification, but there are some synergy associated with the use of the hydrogen heating and with the hydrogen assets for other roles that has to be taken into account. And that will that with having the hydrogen for heating, that will create hydrogen demand for other hydrogen assets. So this slide shows the kind of the role of different hydrogen technologies. So different hydrogen technologies will have a different role in the system, and they have to play together in order to optimize the whole system operations. And this synergy has to be taken into account. And the interesting thing is just to highlight one is with the hydrogen boiler as a mean to decarbonize the heat at the kind of like can be at the domestic and then commercial sector as well. That's actually can also play part in the synergy with the whole system or the whole hydrogen system. So that's which then make the study shows that the hydrogen heating is actually quite found competitive from the economic point of view against the full heat electrification. Now this slide provides, so from the model, we can then also analyze the annual system costs for these two different scenarios. So with the hydrogen for heating, you can see that the annual system cost is 85.6 billion. This cost include the whole electricity sectors, infrastructures from the capex and the opex of the electricity generation network, OPEX electricity, storage, and so on. This also cover the cost of the hydrogen system from the hydrogen and carbon capture storage system, the capex and opex, and also the heat infrastructures, and also the cost of the flexibility technologies required, such as like a demand response. And we can see that the hydrogen for heatings, the annual system cost is lower compared with the full heat electrification. And it is primarily because with the hydrogen for heatings, we will discuss this a bit more detail, but you can see that the cost of the electric heating in this case, the heat pump is quite large. On the right-hand diagram here, it shows the primary energy supply for these both scenarios. So with the hydrogen for heating, this will require more than 1,000 terawatt-hour per year energy, compared with around 840 kind of the terawatt-hour per year in the full heat electrification. And that's expected because with the heat pumps, the efficiency is much higher compared with the efficiency of the gas boiler. So the overall energy system efficiency in the full heat electrification is much higher, more than 100% compared with around 80% in the hydrogen for heating. But because this is achieved by investment in the more expensive heating technologies, then and also the system integration cost of the heat pump is much higher compared with the hydrogen boiler, then the cost of the system is actually higher in this context. So a system with higher energy efficiency will not always lead to a more cost-effective system. That's one of the key findings of the studies that we carried out. So this is the difference between the hydrogen for heating and then full heat electrification. So with the hydrogen for heating, we can reduce the need for investment in low carbon generation and also the distribution. It is associated with the smaller electricity peak demand. We can also reduce the investment in the heat pump, which is quite high, and also other electric heating, and also the flexibility requirement to support the heat pump, such as the heat storage. But on the other hand, we have to increase the investment in the blue hydrogen production from autothermal reformer with the CCS, there will be some increase in the carbon storage requirements and also the use of the gas to produce the hydrogen, and the investment in the hydrogen boiler, and we have to maintain also the gas network. So this slide shows the impact of these two different scenarios, hydrogen for heating and full heat electrification, on the power generation capacity portfolio, where we can see that in the heat electrification scenario, there is a significant increase in the requirement of the generation capacity associated with the increase in the electricity peak demand, which is shown on the right-hand side. So in the full electrifications, the electricity peak demand increased to 115 gigawatts, while in the hydrogen heating, this is only up to 87 gigawatt. So this is implication or the system integration cost of the heat pump, for example, that also need to be taken into account when we consider how the heat in the UK should be decarbonized. So this slide shows kind of like 7 days in the winter peak week, where the system is stressed on day 16 to 18 because of it is a very cold conditions. So the temperatures plummeted into -6 something, and then also at the same time there is no wind. So you can see that the offshore wind here produce very little compared with the kind of like with the normal days. So in order to cope with this event, then the system has to start operate with the gas CCS, but also with the hydrogen power generations here. In addition, with some support from the interconnection and importing power from the neighborhood countries. While on the other hand, when moving to the next day, there is a then significant wind increases, wind output increases that, and then there is a balancing issue in this context, where then the electrolyzers will be able to support the supply-demand balance by absorbing the excess wind output and produce the hydrogen. So the role of these technologies, hydrogen technologies, are quite different, but they have to play together on the system level in order to minimize the overall system cost and in order to support cost-efficient system operation. This is the same with the heat electrification pathway, but of course with the heat electrification pathway, because of if you look at the peak demand in the heat electrification pathway reaching significantly higher compared with the hydrogen pathway. So there will be a lot of increased requirement in the hydrogen generation capacity needed. And that's the reason why the slide previously showed there is a trade-off between the use of the hydrogen heating and also the hydrogen power generation, because if the system doesn't use the hydrogen for heating and use electric heating, for example, which require a lot of which increase the electricity peak demand, this has to be compensated by using higher volume, higher capacity of the hydrogen generation. So this slide also, from the model, we can also analyze from the demand and the supply of the hydrogen. So the demand of the hydrogens in the hydrogen for heatings come from three main sectors. One is the hydrogen used in the power generation, which is relatively kind of like small compared with the overall annual hydrogen demands. And the biggest demand is actually come from the hydrogen for heating at 230 terawatt hours. While there is 125 terawatt hours per year associated with the hydrogen demand from the industrial processes with the large transport, shipping, and aviation, agriculture, and so on. While in the full heat electrification, of course, this demand disappeared. And this on the right-hand diagram here showing this how the optimal hydrogen productions portfolio, that we can see that 232 terawatt hours will come from the blue hydrogen, and this is of course depend on the assumption, on the gas assumption that we use in the study, which we use the projection from the national grid in 2050, and some from 63 terawatt hours from the electrolyzers from the green hydrogen, and 96 terawatt hours from the biomass energy with the CCS producing hydrogen. And we can see that much smaller production coming from for the second scenario, but it's still remaining that these three technologies remain to be used in the second scenarios. And this is the optimized hydrogen production mix, and this is the capacity that associated with the hydrogen production on the previous slides. But this is the capacity factor, and I just would like to highlight that with the BECCS producing hydrogens, that this is kind of use almost 100% the capacity factors, because the availability of the biomass is quite limited, and this provides the negative emissions. This can be considered as negative emission technology, which is needed to offset the emission from the hard to decarbonize sectors, and this operates like full flat the whole year round. While the ATR, the CCS in the hydrogen technology, hydrogen heating scenarios has around 52% capacity factors, but of much lower, less than 20% in the full heat electrification. But this capacity will still be needed, because in order to support the hydrogen power generation during the peak demand period. So this is again highlighting the need to see the impact on the whole system, and how this, in the hydrogen heating scenario, there is a synergy with the hydrogen heating, which then increase the utilization factors of the other hydrogen assets. So this is kind of the GB emissions and the carbon sequestration's performance of the two systems. So in both scenarios met the net zero carbon targets. So there are some residual emissions, a very small emission from the blue hydrogen process, and this is offset by the use of the hydrogen BECCS and also the hydrogen in the power sectors. While in the full electrification, then there is a more substantial shift from the biomass energy to the power sectors, which we can see here that the negative emission from the power sector increases, while the negative emission from the hydrogen production from the BECCS, hydrogen BECCS, becomes less. And of course, with the hydrogen for heating, because of the blue hydrogen productions, it will require more substantial volume of carbon capture and storage. So this is my last slide before the conclusion. So we also run a large number of sensitivity study in order to understand the robustness of the results, the conclusion, because of course the results will be scenario specific depending on the assumption that we put into the model, and the model is actually also is also deterministic, assuming the perfect forecast of everything. But then, in order to understand this robustness, we evaluate with different gas prices, with the hydrogen mix policies, hydrogen storage costs, domestic heat, level of the domestic heat in the system, whether there will be high flexibility or low flexibility in the system associated with the customer participation in providing demand response, and also the distributed storage. We also try to analyze based on the different cost of technologies, like cost of the offshore wind and cost of nuclear, and also different interconnector capacity, and also stress the system with different weather events, such as that in the winter there will be less wind power, wind energy, and also the duration of the extreme events, where previously I just showed around three days extreme event, but we extended to 1 week and 2 week, and what will happen. So the blue bar here is the annual system cost of the hydrogen heating scenario, and the orange one show the annual system cost of the heat electrification, and they will vary according to the different assumption that we put into the model. And one which is quite interesting is that it's also surprised us in the beginning, is that in all scenarios that the hydrogen for heating, actually the annual system cost of that is lower compared with the full heat electrification. But of course, this will have the gas prices, for example, is the assumption on the gas prices is quite sensitive to the hydrogen for heating, and this will increase the system cost more than in the full heat electrification. But once the gas is very high, the gas price is very high, then the model will switch from the use of the blue hydrogen to the green hydrogen. Another finding is also associated with that the flexibility will be important in both cases, whether it is hydrogen or full heat electrifications, because there are some thought outside there which say that, okay, if I use the hydrogen for heating with the less electricity demand, then the flexibility will becomes less requirement, and that will be less required. That's maybe not absolutely correct, because in here we can see that with the flexibility, it is still reducing substantially the annual system cost. And we also, when we increase the duration of the extreme weather event, this is actually not a significant issue, because then the system already have some sufficient capacity from the CCS, hydrogen, and nuclear power generation in order to cope with that. So sorry for a bit overrun, but this is just a final slide. It's a conclusion. So from the studies, we concluded that the hydrogen will play a crucial role in this cost-effective energy system decarbonization, but we have to take into account all the role of the hydrogen, not only for the energy decarbonization, but also to provide flexibility, to provide to improve the energy system security, resilience against extreme weather events, in order to minimize the overall system cost. So all hydrogen technologies will have a specific functionalities, but they have to work in synergy with other low carbon technologies. And it is also one of the key findings is that we found that hydrogen heating is quite competitive against the full heat electrification from the techno-economic point of view. And the results are actually quite robust, even in the case of extremely high gas prices. And from all these sensitive studies, the range that we can see that the hydrogen pathway actually can save between 2 to 7.3 billion per year compared with the heat electrification pathway, depending on the scenario. And another point is that to re-highlight is that a system with higher energy efficiency will not always lead to a more cost-effective system. And the whole system analysis and optimization in planning on operating future energy system will be needed in order to empower the hydrogen. Because if we consider the hydrogen, whatever the application is, with the siloed approach, that will lead to suboptimal solutions and also suboptimal policies. So if you are interested with more detail about the studies, you can download the paper with the link or with the report in the that's available on the website. Thank you for listening.
Thank you very much, Danny. Really interesting presentation. I would like to start with 2 questions from my side, and then ask Eugene and other colleagues to ask questions they have. My two questions, one of them is about energy storage, and I'm interested to learn more about how your model distinguish between different types of energy storage with different technical characteristics. And in particular, I'm referring to long duration storage and also storage technologies kind of more suitable for diurnal balancing of supply and demand. So this is one question. And the second question is about your assumptions related to transportation of hydrogen. If you're assuming you're going to continue using the existing gas network for transporting hydrogen, or if you're assuming that you're going to develop completely brand new hydrogen pipeline. So this is the second questions, and related to these questions, I'm keen to understand if you have any decommissioning cost in your model. So in the case that you are not going to use the existing gas pipelines, do you have any cost associated with decommissioning of those assets? Yeah, let me stop here, but if you forget my question, I'm happy to repeat that again.
Yeah, thank you, Mr. So regarding the energy storage, the model considers a number of different technologies. So of course, from the electrical storage, we have pump hydro storage. We also have the batteries connected at the distributions, and from the hydrogen storage, we have the underground storage, which are quite site specific. It's just only in number of different locations on the GB, but we also consider the medium pressure distributed storage, which can be anywhere. Of course, all of those will have a different technical characteristics, such as the efficiency and also the cost. We also, for the storage, we also consider the heat storage, like the thermal storage, and this is particularly important to support the operation of the heat pumps. And the heat storage can also be quite large, especially for the district heating thermal storage. And that will be also provide some flexibility to the electricity system. So all storage technologies there are considered in the model at the moment. Regarding the transportation of hydrogen, we consider transportation of hydrogen using the pipes. So the national transmission system, there are two scenarios that we can consider. One is the use of like both the gas and also the hydrogen. But for these studies, we consider that the national transmission gas system will be retrofitted, will be transformed into the hydrogen pipeline. But we can do both. So there is also another implication of that, because then if there is no gas, then the gas plants, for example, like the gas CCS and also the autothermal reformers, for example, they can only be located in the region which has the gas terminal. So it's normally near the sea. And with also the carbon storage there. Now with the distribution network in the hydrogen for heating, we assume that the gas distribution is converted to the hydrogen distribution, and we manage the kind of like the similar costs of maintaining the gas distribution there. In the full heat electrification, we assume that the gas distribution, only the gas distribution will be decommissioned, and we take into account around maybe, if I'm not mistaken, £1 billion per year cost of decommissioning the gas in the full heat electrification. I believe that's address all your questions. If not, please let me know.
That's correct. Thank you very much for the answer. Eugene, would you like to come in? Do you have any question you would like to ask?
Yeah, my question was, and I know it's not directly related, but have you considered also the sort of the cost of life cycle of the emissions? Did you take into consideration while doing the study, or was just pure on technology portfolio based?
I just would like to understand a little bit more when you mentioned about the life cycles. Is it like the emission upstream, you mean, or?
Yes. So basically, I know it's a complicated issue, but maybe it's the next steps. But let's say when you compare the costs for autothermal reforming production with CCS compared to electrolysis, let's say, is this and in terms of the carbon footprint for both technologies, did you compare those or not really?
Yes, definitely. So in this context, for example, if you can see that this is the carbon emissions, this is residual emissions from the autothermal reformers with the CCS, because the autothermal reformers, the CCS, the carbon capture that are quite efficient, can capture like around 96% of the carbons. So it's only 4% released to the atmosphere that need to be offset by negative emission technologies. But of course, this also will require the more substantial carbon storage for the hydrogen for heating. Because you can see here that the reformers, this is the carbon captured in the reforming process to produce the hydrogen. So this cost, there is cost associated with the storing carbon and also the cost of building all these negative carbon emission technologies infrastructures. So that has been taken into account in the model.
Yeah, because the reason I'm asking this a little bit deeper is, when we considered building, when we designed the hydrogen hub system here, we looked into also the grid electricity that would be needed to do the hydrogen production with electrolysis, because if you have renewables online that could be used for electrolysis production, it could be used only a fraction of a day and not to the full capacity. And so then the grid has to come in, and the grid has a different footprint, and if you compare the outcomes, the picture is quite complex. But my question would be, if you looked into deeper into the kind of more holistic view for the carbon cycle within the system, and if you have any idea what would be better, do you think the autothermal reforming with CCS, regardless of how much you need to store, can it be compared to the electrolysis today? Not like in 30 years, but today.
I think this is a very good question. So the model, so if I can capture correctly the question, so the model can capture also the impact of distributed hydrogen technology. So for example, like if you put the hydrogen at the electrolyzers or the fuel cells at the distribution, how this will impact on the distribution network capacity requirements, for example. That's not on my presentation, but we have other studies that address those kind of the questions. So the impact on the electricity distribution is also part of that. But in here, we for example, I just show that using the hydrogen heating, that can reduce the distribution network capacity reinforcement requirement compared with the heat pump, for example. So that's choosing whether you use a heat pump or the hydrogen heating also affect the local electricity capacity requirements.
Yeah, it makes sense. I understand. Thank you.
Yeah.
Good. Thank you very much, Eugene. I think we are, I cannot see actually any questions in Q&A box. So if there is no other question, we can conclude the webinar here. I would like to thank you again, Danny for taking time, giving this presentation to us, really insightful. And thanks a lot to everyone joining us in this webinar. Many thanks.
And please don't forget, there's a next webinar series coming up. This is episode 7, and this time is going to be on reliability of the US electricity grid and the prospects for hydrogen as generation fuel source by Kara Franstrom from School of Energy Resources, and she is a director of SERPA, which is the Center for Economic Policy at School of Energy Resources.
Thanks a lot, Eugene.
Okay, thank you.
Thank you. Bye.